Hello friends, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture we will discuss collision in two dimensions, little bit concept and few examples. So let's start. So you can see collision in two dimensions. There we will discuss the collision along the x-axis as well as y-axis, right? Actually we will conserve the linear momentum along the x-axis and conserve the linear momentum along y-axis to just solve the numericals. So let's start with the concept. We have two objects, mass m1 and mass m2. Usually in the examples also, the mass m2 is called the target, or initially it was at rest. Usually, it's not always possible, but sometimes it is at rest in the numerical situations. So here, this m2 is at rest and m1 is moving with some speed v1 initial. So after the collision, let's say m2 start moving in this direction with some different speed v2 final, and the m1 starts moving in this direction with some speed v1 final. So this is v2 final, this is v1 final, right? And they are making some specific angles theta 1 and theta 2. So let's see how we can write the equation for conservation of linear momentum along the x-axis and y-axis. So we can say along x-axis. So along x-axis, we can write the linear momentum of m1, that is m1 v1 initial, because m2 is at rest, so the linear momentum of m2 will be 0 before the collision, and after the collision both are moving, but we have to write the equation along the x-axis, so we will write the component of this momentum along this axis. So it will go with m2 v2 final cos of theta 2. So we will write it m2 v2 final and cos of theta 2. Similarly, for the other, we can write m1 v1 final and cos of theta 1. So this is the linear momentum equation along the x-axis, conservation of linear momentum along the x-axis. Now along y-axis, we can write, you can see here, initially or before the collision there is no particle which is moving along y-axis, so we will write 0 plus 0 along y-axis before the collision, and after the collision it can be written as m2 v2 final, because there is a component of this momentum along the y-axis in terms of sine of theta 2. So we will write m2 v2 final sine of theta 2. Then we have the linear momentum here with the component along the negative y. So that's why I'm writing the negative sign, negative. So it is m1 v1 final sine of theta 1. So as this is a negative sign, we can easily write the situation something like this. So we can write it as m2 v2 final sine of theta 2 is equals to m1 v1 final sine of theta 1. So this equation can be treated as our second equation. So one more equation we can write here if the collision is elastic. So if collision is elastic, then we can write the conservation of kinetic energy. So conservation of kinetic energy says the kinetic energy before the collision is equals to the kinetic energy after the collision. So in this situation, the kinetic energy before the collision can be 1 by 2 m1 v1 initial square plus 0 is equals to 1 by 2 m1 v1 final square plus 1 by 2 m2 v2 final square. So this is the equation we can use to solve our numerical, but only in case of elastic collision. We can write the conservation of kinetic energy, that is the kinetic energy before collision is equals to the kinetic energy after collision. Let's use these equations to solve the numericals. So our numerical number first. So we have a numerical number first here. You can see two particles of equal masses have an elastic collision, right? Keep in mind we have an elastic collision, the target particle being initially at rest. So let's draw the situation. So let's say this is our target particle which is at rest initially, right? And the other one is moving with some speed. So it is moving with some speed. So m mass is the mass and vi, this is the momentum. So what will happen? You can read the show that unless the collision is head on. So if the collision is not head on, then what will happen? The two particles will always move off perpendicularly to each other after the collision. If the collision is head on, then both will move along the one dimensional motion like this. They will move after the collision in this line. But if the collision is not head on, then what will happen? One move in this direction and other move in this direction. And if their masses are equal, then the angle between them must be equals to 90 degrees. So we have to prove this, because in this situation the angles are, the masses are equal. So obviously they will move at perpendicular. This is the straight fundamental line you can use, but we have to prove it why, how they will at 90 degree. So after the collision, the situation something like this. So this is our initial direction of motion, and after the collision one is moving in this direction and other one is moving in a perpendicular direction. So let's say one is moving in this direction, okay, and other one is doing in a perpendicular direction. So it is m2 v2 final, and this is m1 v1 final. Okay, so there is no need of calculations. We will use the vector approach to solve this situation. Okay, look at carefully what is happening here. So collision takes place. It means the conservation of linear momentum is conserved here, is valid here. It means the vector or the linear momentum before the collision is equals to the total linear momentum after the collision, right? Or you can say the vector of linear momentum before the collision is must be equals to the vector sum of the linear momentum of these two particles after the collision, because the momentum must be equal before and after the situation. So we can draw this one in terms of vector form. So in terms of vector form, we can say something like this. So this is our resultant. Resultant means the initial momentum, mv1 initial, right? Because it is in this direction. So I draw this one, and the other two must be the vector sum of this. That is, the vector sum of this momentum and this momentum must be equals to this one. So let's draw them. So one is, you can see one is in this direction, right? So you can write it as m2 v2 final, and the other one is in the downward direction. So you can draw in the downward direction something like this. So it is m1 v1 final. So there is an angle, this angle phi we need to calculate. Okay, so this is the angle theta, this is angle theta. So we need to calculate phi, because phi is the angle between this one and this one. This is phi. Okay, so this diagram or this triangle in terms of vector approach is in terms of momentum, but when the masses are same, we can remove the situation. So when the masses are same, what we can write? We can write m1 v2 final vector equals to m1 v1 initial, so we will write the resultant first, that is m1 v1 initial vector is equals to, then the other two, m2 v2 final vector plus m1 v1 final vector. So this is the conservation of linear momentum in this situation. Okay, masses are same, we can remove the masses because m1 equals to m2, let's say it is m, so masses can cancel, so m1 m2 all these terms can cancel. So what we have, then we can write v1 initial vector equals to v2 final vector plus v1 final vector. So this is what we get after removing the masses. All right, so we can draw the situation here again. You can see in terms of velocity, this is the v initial, right, which act as a resultant, and this is the velocity vector after removing the masses. This is the velocity vector v2 final, and this is the velocity vector v1 final. Okay, again we need to calculate this angle phi. Okay, so what you see when you apply the triangular law here, so this is the resultant. It means the vector sum of this one plus this velocity must be equals to this velocity. This is what it is saying. So here again you can see this triangle is completely represented by this equation. They are equivalent, the equation and the corresponding triangle. Now, as the situation is elastic, we can also conserve the kinetic energy. So in terms of kinetic energy, so conserve kinetic energy. So once we conserve the kinetic energy, what you see, you can see the initial kinetic energy, that is before the collision, 1 by 2 m1, or you can simply write mass, and initial velocity v1 initial square is equals to 1 by 2 m v1 final square plus 1 by 2 mass v2 final square. Again you have a chance to remove the quantities like mass term, we can easily remove mass term, mass and mass. Similarly half can cancel. So what you have, you can write v1 initial square, that is the resultant, is equals to v2 final square plus v1 final square. So this is the situation you can see here, this situation. So what you understand from this equation, it is something like Pythagorean theorem, right? So what it says, this vector square or this side square, because it's a triangle, so this side square plus this side square is equals to this side. What it means this is acting as a hypotenuse and this acting as a perpendicular and this act as a base. So it represents like base square plus perpendicular square is equals to hypotenuse square here, right? So it is Pythagorean equation or theorem. Okay, so Pythagorean is valid only v2 final vector is perpendicular to v1 final vector, right? Because if this is a right triangle, then only this equation is valid. So it means that the base and the perpendicular are at 90 degree. It means the phi, this phi is 90 degree. So obviously if this is 90 degree, this angle is also 90 degree. So we can easily say that the v2 final and v1 final are at 90 degree. So this is what we need to prove, that if the masses are same and the collision is elastic, then what will happen, both the masses will move in such a direction that they are making 90 degree with each other. So this is the 90 degree they are making with each other. So this is how we can prove this situation without further calculation, just with the approach of triangular law. Okay, let's move to the question number 2. So this is our question number 2. You can pause the video, you can write the question completely, then try to solve it and check the solutions. Okay, so what it says, we have two objects MA and MB both are moving initially before the collision, right? But in different direction. MA is moving along x-axis, MB is moving along y-axis with some specific velocities. You can see the velocities are also given, masses are also given. But what is happening here, after the collision which takes place at the origin, they start moving together with some common velocity at an angle phi. Okay, so you can see collision is perfectly inelastic and takes place at the origin. So our first question is A part, find the velocity of combined mass after collision. So we need to calculate VC. So with the help of conservation of linear momentum, we can write the answer. So write the conservation of linear momentum along the x-axis and y-axis. So along x-axis. Okay, so along x-axis we can write MA and VA along x-axis plus MB VB is equals to MA plus MB with common velocity, and cos of phi. What is cos of phi, right? So the linear momentum along the x-axis goes with cos of phi. So this is our equation number first. This is our equation number first. I missed something. Yes, here, because this is not along x-axis. Now along y-axis. Along y-axis. Along y-axis, what you can see, only B particle is moving. So we can write the equation MBVB is equals to the sine component MA plus MB common velocity with sine of phi. So this is our equation number second. Now you can divide these two equations to get tan of phi, because we have sine of phi, we have cos of phi. So two equation divided by equation number first. So 2 divided by first. So what you see, you get tan of phi is equals to MB VB divided by MA VA. So tan of phi, let's put the values. So your values are given. MB is 55 and speed is 8 km per hour, sorry 7.8, and MA is 83 and the speed is 6.2. So once you solve this situation, you will get phi equals to approximately 40 degree. Tan inverse this, you will get phi is equal to approximately 40 degree. So in this situation, we have calculated the value of phi. Now we will use this phi. We will use this phi. Let's say in our equation number second, we will put the value here to get VC. Okay, so put phi equals to 40 degree in equation second. So once you use it, what we have MB VB divided by MA plus MB sine of 40 degree equals to VC. Let's put the value. It is 55 kg multiplied by 7.8 divided by mass term. MA is 83 kg and 55 kg and sine of 40 degree equals to VC. Okay, so once you calculate all this situation, you get the answer. So your answer VC will be 4.836. It is kilometer per hour, because the velocities are given in kilometer per hour. So this is the situation. So obviously, if you are not allowed to use the calculator, the sine or tan of phi value must be given to you in your question, and sine of 40 degree must be given to you. Okay, so this is our answer for this for this part. So let's move to part number B. So what it says, what is the velocity of center of mass? What is the velocity of the center of mass of two objects before and after the collision? So this is the situation before the collision. You can see both the particles are moving in their respective directions, and after the collision they are moving together with the same direction. Okay, so it is easy to conclude that the center of mass velocity, the center of mass point, is also moving with this combination. If the combination is moving with the velocity we just calculated, vc, that is, this combination is moving with vc, so it means that this is vc velocity. So center of mass point is also moving with the same velocity in the same direction, right? So after the collision, center of mass velocity is also moving with the same velocity vc, with the same velocity vc we calculated in part A, okay. But what about before the collision? What is the velocity of center of mass? Okay, so keep in mind that during the collision there is no external force acting on the system. That's why the momentum is conserved, right? As no external force is acting on the system, so there is nothing which can disturb the velocity of center of mass. It means that the velocity of center of mass after the collision and the velocity of center of mass before the collision will remain same, because nothing is disturbing the velocity of center of mass, as there is no external force acting on the system. So due to collision, the velocity of center of mass does not change. So we know the final value. So it means the before the collision, the center of mass velocity is also the same, that is vc, okay. So as no external force is acting on the system, so center of mass velocity will remain same even before the collision. So we can say as no external force is acting on the system, so velocity of center of mass will remain same, that is, velocity of center of mass before and after the collision is equals to vc, and having a value of 4.836 kilometer per hour. So this is the velocity of center of mass before and after the collision, this one. All right, so I hope you understand this concept. Now let's move to part number C. What it says, what is the fractional change in the kinetic energy of the objects because of this collision? So we need to calculate the fractional change. Fractional change means what? Fractional change means final kinetic energy negative initial kinetic energy divided by initial kinetic energy. This is what we need to calculate. So let's calculate the initial kinetic energy first. So initial kinetic energy of the system is equal to 1 by 2 ma va square plus 1 by 2 mb vb square. So kinetic energy initial is equals to 1 by 2 multiply mass is equal to 83 and speed is equal to 5.2 square plus half, mass is equal to 55 and speed is equal to 7.8 square. So you can solve this equation to get the kinetic energy. You will get 3270 kg kilometer square per hour square. So this is the kinetic energy you will get after the calculation initially. Okay, now what about the final kinetic energy? Similarly, we can calculate the final kinetic energy. So K final, again the system is moving combinedly, so we will write 1 by 2, and the combined mass is equal to 83 plus 55, and the velocity, that is the combined velocity, will calculate 4.86 square. So you will get K final is equals to 1630, then again the unit kg, kilometer square per hour square. So this is the equation you will get. This is the kinetic energy after. Now fractional change. How you will write fractional change? Fractional change in kinetic energies. So fractional change in kinetic energy is K final minus K initial divided by K initial. This is the fractional change in kinetic energy. Let's put the values. K final is equal to 1630 and K initial is equal to 3270 divided by K initial 3270. Okay, once you calculate it, you will get negative value and 0.50 with no unit, because the unit get cancelled. So what does it mean? It means that a negative sign represents the loss. So it means that 50% of the initial kinetic energy is lost as a result of the collision. So what it conclude? It conclude 50% of initial kinetic energy is lost as a result of the collision. So this is the answer of this question. Okay, let's move to question number 3. Question number 3 says two balls A and B having different but unknown masses. Okay, their masses are not same. So we have A, we have B. B is moving with some velocity V, and A initially is at rest. This is the situation before the collision. So A is initially at rest and B is moving with speed V. After a collision, B has a speed V by 2 and move perpendicularly to its initial motion. So this is the initial motion, and perpendicular, this is the motion after the collision with a speed of V by 2. Okay, so it says find the direction in which ball A move after collision. So we need to calculate this direction phi. Alright, it is not difficult question. Let's conserve the linear momentum to solve this situation. So we will write the linear momentum along the x-axis and y-axis. So let's solve it. So linear momentum along x-axis. So along x-axis. Along x-axis you can write only B is moving. So mass of B with speed V is equals to, along the x-axis, this is not along the x-axis, only a part of this linear momentum will be along x-axis, that is MA VA cos of phi. So what you will see, MA and VA cos of phi. So this is our equation number first. Now we can write equation number second, that is MB, and this equation number second is along y-axis. So I'm writing along y-axis. So let's write along y-axis. So if you know all this small stuff, you can increase the speed of the video. Okay, so along y-axis, initially or before the collision there is nothing, so you are writing 0, and after the collision what you need to write, you can write the linear momentum, this which is upward, so positive, and the component of this along the negative y direction. So the component of linear momentum of this system in the negative y direction will be negative. Okay, so I'm writing it is mass of B and speed is V by 2 then negative sign, mass of A, V of A, and sine of phi. Sine of phi. This is our second equation. Now we can simply divide to get the tan of phi. So divide our equation second divided by first. Okay, second divided by first. What you get? You get MAVA sine of phi divided by MAVA cos of phi is equals to MBV by 2 and MBV. So you can see here a few things can cancel, like MVB here, this and these terms are cancelled. So you have sine phi divided by cos phi is equal to tan phi is equals to half. This is what you get. So phi is equal to tan inverse half, which you can write equals to 26.5 degree. So again I am repeating, if calculator is not allowed in the classroom, then this value must be given to you. This is the value of phi. So what they are asking, find the direction in which ball A move after the collision. So this is the direction made by the ball wave with the x-axis. This is the direction made by A with the x-axis, after collision. Okay, so this is our answer of this question. So let's move our next question. So next question is, after a completely inelastic collision, two objects of the same mass and same initial speed, okay, they have same masses and same initial speed. You can see mass and velocity are found to move away together at half their initial speeds. So initial speed is v, so half their initial speed is v by 2. They are moving combinedly, so the mass will be 2m. Find the angle between the initial velocities of the object. So we need to calculate this angle, that is 2 theta. What is the angle between their initial velocities? So again, our simple approach is conserve the linear momentum along x-axis and y-axis. So let's start along x-axis. Write the conservation of linear momentum. So the linear momentum mv cos of theta, then we have along the x-axis mv cos of theta, and finally we have the combined one, that is equal to 2 mass, this one m, and speed is equal to v by 2. So from this equation you can see, so when you combine this equation, you will get 2 times of mv cos of theta is equals to 2m v by 2. So few things can cancel here, m can cancel, 2 cancel, speed cancel. So you have cos of theta is equals to 1 by 2. So theta is equal to cos inverse 1 by 2. So it means theta is equal to 60 degree. So you get theta is equal to 60 degree. So what is the angle between them? So this is 60 degree and this is also 60 degree. So the angle between the initial velocities of the objects will be 120 degree. Okay, so we can write the angle between the initial velocity vectors will be 120 degree. This is the answer of this question. So this is all about today's lecture. I hope you understand this, you enjoyed this. See you in the next lecture. Till then, bye bye.